You apply a voltage difference to a conductor. The electric field exists in the conductor. Charges move. You get a flow of charge. We call it a current. Now the question is, how much current do you get? That's what we want to know. And the way you know is from Ohm's law. So let me give you sort of a definition of Ohm's law. Well, actually, Ohm's observation that is relevant to materials of interest in 1827. J equals sigma E. So first, let's talk about the commentary here. This is not a law, okay? So you learn as a child that in science we have theories, those are ideas, and we do experiments to test them, and then if they always work, then we promote it to the level of law. Right? That's a nice story, but it's almost the opposite is true for some reason. It seems to never work out that way. Plenty of things are called a law. Ohm's law is called a law. It's not a law. Not a single material exactly obeys Ohm's law. No material. Many materials approximately obey Ohm's law, but it's not really a law. Many things that are laws are still called theories. Relativity theory. If anything is a law, it's relativity. But we often still put theory on there. Have you ever heard anybody say relativity law? No. Evolution, the theory of evolution. Well, there's probably a good reason a lot of people call that theory. Let's not get into that one. But there are a lot of laws and theories where it's completely backwards. Let me give you another. Ohm had two laws. There's also Ohm's acoustic law, which states that a musical sound is perceived by the ear as a set of pure harmonic tones. It is well known to not be quite true. Right? So there you go. Law, theory, forget that thing you were told as a child about theories and laws. So this is not an exact law, but it'll work. It's good enough for what we're going to be doing. And it is then that the amount of current you get in terms of current density is simply proportional to the field that you apply. Now, I know you're used to thinking of V equals IR, and we'll get to that on the next board. But actually the way it was originally stated was not in terms of voltages and currents, but in terms of current density, the current per unit area, and electric fields, not voltages. Of course, we know they're very closely related. Another thing to keep in mind, oh, and then the thing to keep in mind is that sigma is the conductivity of the material of the wire, say, or the material in the wire. Okay? And it's in a unit that we'll talk about more in a minute of inverse ohm meters. So we use omega to talk about resistivity and conductivity in inverse ohm meters. Sigma is not the surface charge density in this case, okay? There are only so many Greek letters, and we reuse them. So first part of the class, sigma meant coulombs per meter squared. It was a surface charge density. Now sigma means the conductivity. And you just have to use context sometimes to know which one we're talking about. Usually when they give you a number and they give you a unit, then you can tell. We try not to have a single problem with both sigmas in it, but I can't make any promises. I've seen it happen in textbooks before. Okay? So anyway, that's Ohm's law. Now let's see if we can put it in a more useful form. Tricked you. In circuits, we usually don't think about the conductivity, we think about the resistance. That's what you're used to thinking about, the whole V equals IR. So let's see if we can get from the conductivity to the resistance. Let's draw it out here. Let's see. So I'm going to draw a nice big wire like that, and it has some cross-sectional area A. And let's see, it has some conductivity. The material has a conductivity sigma, and it has some length L, like that. We want to make current flow, so we've got to put a battery on here. So here is a battery, delta V between its positive terminal, its negative terminal, comes up here, touches that face. This one comes back here, and touches that face. So we know what happens. That sets up an electric field, and it makes a current flow, and current is always from the positive side to the negative side. So instead of sigma, let's see what else we could say about this. So we know we have Ohm's law, J, the current density, current per unit area, equals sigma times the electric field. So let's see. So we know for a wire, for sort of this conducting wire, E actually is always delta V over L. Okay? In a parallel plate capacitor, you would have a nice uniform field like that. Well, it turns out inside of a metal wire like this, you also get a fairly uniform field, even if you start bending up, bending up the wire. So we can substitute that for E, and then let's see, we can also substitute I over A for the current density. Right? That's the definition of current density, equals sigma, and then E is the voltage difference over the length. And now we have the parts of this that we like when we're used to thinking of delta V, potentials and currents. We just rearrange this, and you get what? You get delta V that you like is equal to a bunch of stuff times I. It looks like L over sigma A. Right? And that's actually the Gauss's law, or the Gauss law, the Ohm's law you're used to. V equals IR, V equals I, and this must be R. So this R for the wire is L over sigma A, is the resistance of the wire. And you can see what unit it must be in. It must be in volts per amp. But we have a special name for that, and that is the ohm. So ohm, even though he really didn't have a law, he really didn't have two laws, he did get something named after himself, and that is the unit of resistance, ohms, and it's written with an omega, which is easy to remember. This is a good time to review the difference between intrinsic and extrinsic properties. So let's make sure we remember intrinsic and extrinsic. Wow, okay. Intrinsic, extrinsic. So intrinsic depends on sort of the material only, if we're talking about material properties. And extrinsic, again, talking about material properties, depends on material and size, shape, mass, etc., amount. Okay. So the best example, if you want to compare just in your head, is density is an intrinsic property. Density is just the amount of mass per unit volume, whereas if you actually had an object, it has an actual mass, right? So this does depend on the density, but also on how big it is, what's its volume. So its density times its volume would give you its mass. So there's actually 4 quantities to throw around when you're thinking about resistivity. So I want to make sure it's clear the difference. The first one we did was an intrinsic property. It was the conductivity. Okay, the conductivity sigma, and it was in 1 over ohm meters. So that's how Ohm's law is stated. It's stated in terms of an intrinsic property of the material. We also use that to get to the resistance. All right. The resistance was R in ohms. And the resistance of a wire is really an extrinsic property. It depends on what kind of wire it is. It depends on the conductivity of the wire. But it also depends, remember it had the length in there and the area in there. The longer the wire is, the higher its resistance. That kind of makes sense. The bigger the cross-sectional area, the lower its resistance. And that kind of makes sense. More places for the current to go. So these are the 2 we've talked about, but they're not the inverse of each other, actually. So there's 2 more that we could define. One would be, if we have a resistance, an object must have a conductance. Okay, that's usually G, and it's actually in a silly unit. It's inverse ohms. It's called mhos. You don't see it too often, but it is in mhos, or you could write it as ohm to the -1. So if these are the inverse of each other, there must be an inverse of conductivity, and there is. It's the resistivity. And the resistivity, we usually write, you're going to hate this, with rho. So this is not the surface charge density, and this is not the volume charge density. This is the conductivity in this case, and this is the resistivity of the material. So these are inverse of each other. Rho equals 1 over sigma. They're really the same thing. There's no difference. It's just whether you want to think about it as conductance or resistance. And these are also the inverse of each other. R equals 1 over G. Now when we do problems, so especially in freshman physics, we almost never use this. This is pretty rare. We won't think about that. We'll think about resistance. And then when you're calculating a resistance, you'll look up a table for the properties of the material, and half the time it'll give you conductivity, half the time it'll give you resistivity. But there's no difference in the information. You just got to invert it or not. All right? So there's 4 actual terms. Keep them all straight in your head. 2 are intrinsic, the ivides are intrinsic, and the anses are extrinsic. So if we think about our microscopic model for a minute, what's happening in our microscopic model of current and resistance and all this stuff? So let's look at it one more time. Let's see. Big wire here. Everything's fine. Everything's fine so far. Something's going to go wrong, by the way. That's what I'm leading up to. Something is going to go wrong. Terribly wrong. We put a battery on it. No problem so far. I'm happy. Everything's fine, fine, fine. Wonderful. I'm having a great day here. So we put a delta V on it, and we get an E field applied equals delta V over L. I have no problem with that. This has a length L. I can accept that. And we said that the charge carriers, let's get real for a minute and make them negative. I'll let them go that way. E is this way. Negative charge carriers are going to go that way. Of course they're going to go that way, right? The E field is that way. Negative charges are going to go that way. And they're going to fall into the battery, complete the circuit, do chemistry. All that makes me completely happy, okay? So everything is fine. So maybe some of you have noticed what's wrong. There's something wrong, okay? The way we set this whole thing up is we said the electrons are going to move with some constant V drift. Now why would it be constant? That doesn't make any sense. I mean, we have a charge here, it's sitting here, we have an electric field, it's going to feel, this isn't V drift, it's going to feel a force. It's going to feel a force by Coulomb's law. And it's got a mass and it's sitting there, it's going to accelerate like that. And this one's going to start from rest and it's going to get faster and faster like that. It's not going to drift. Where did drift come from? So that's the question. Why did we assign a random or a constant uniform V drift when really they should accelerate? Why is current uniform and constant when it should be always increasing when you apply electric field? So that's a problem. It's been figured out, by the way. This isn't like a fundamental problem and I got to go call CNN and everything. This is known. What we need is an even better microscopic model for current flow in a conductor. And that model is called the Drude model. It's pronounced Drude. I'm not sure why. I'm sure it's related to where he was from. I'm sure someone will correct me in the forums. The Drude model explains why the electrons drift, and it also explains other things. So let's look at the Drude model. Let's see, as a sequence of events, what's going to happen to some poor little electron. And let's look at its instantaneous, its real velocity. Not some average velocity, not some drift velocity. Let's just have the electron sitting there. So let's look at this one. It's just sitting there. Its velocity at time 0 is 0. Right? You apply a voltage. You apply electric field. It feels a force this way. And it does indeed accelerate. Okay? And if it accelerates, that means its velocity increases in time. So it doesn't move at V drift. its velocity just speeds up, and it goes faster and faster and faster and faster and faster. That's what really happens until it collides with the lattice. Oh no, right here, it collides with the lattice. The lattice meaning all the crystalline network of all the atoms that are making up the metal, in this case, if it's a metal. Okay? So it can move along, and you could think of it, it's not really like this, but you could think, you know, if you have a lattice that's nice and uniform, and if you imagine some electron just sitting here accelerating, you know, it can miss and miss, eventually it's going to hit. It's kind of like that idea. You can't get through there forever without hitting something. And now, what's going to happen when it hits the lattice? Well, it's going to bounce off, and if we're doing freshman physics, there's going to be some conservation of energy and momentum, and you can think of it as a billiard ball. It'd be a big mess to think about that. So here's the model. Remember, physics is never, you always use a model. The model in physics is that it just stops. The Drude model says, don't worry about the actual collision and which way it goes and keeping track of all these electrons. That's hopeless. Let's just have a model where we say it stops, and it gives its energy to the lattice. Dumps all its energy in the lattice, and it goes again. Or you could say it does bounce, but the average velocity after it bounces is 0, right? Because it has just as good a chance of bouncing that way as it does of bouncing that way, because all these little billiard balls are bouncing around. So you can think of it as stopping, or you can think of it as being randomized, okay? If the velocity after it hits is randomized, then the average, the typical, if we're looking at a lot of electrons, is going to drop to 0. If you thought of them as all accelerating and then they all collided, when they're accelerating, they all have a uniform velocity moving forward, and they collide and they're all random. So you could think of this as the average velocity of a bunch of electrons. Either way you want to think about it, it did accelerate for a while, and then it stopped because it hit something. Once it hits something, it's just got to pick itself back up and keep going. There's still an electric field, so it's going to accelerate again. Oh, and then it hits something, back down to 0. And it's going to accelerate again. Oh, and this time, oops, same slope. It's this time there was something too close, and it hit early. And then it's going to accelerate again. Oh, it hit something like that. So this is, in the Drude model, this is the trajectory of the electron as it flows through the metal. Is it accelerates, and then it hits, crashes, accelerates, crashes, accelerates, crashes. So what you end up with is, if you were just to not take the average, is it actually floats along with sort of an average velocity that we call v drift. And if we characterize the typical time between the collisions as tau, we can figure out what v drift is. Right? So velocity equals acceleration times time. Okay, so then velocity is going to be the acceleration. What's the acceleration? It's, let's see, well, it's the F equals QE, so it's the force, the QE over M. Sorry, QE over M is the acceleration. And time is tau. We're figuring out how fast does it get. That's tau. So we can write v drift that way as QE over M times tau. So this is why we imagine them having a constant drift velocity when really they're accelerating all the time. They're accelerating and stopping, accelerating and stopping. We saw how the Drude model shows how you actually get an average velocity for the charge carriers when you apply a field. So Drude gives a v drift. Let's think about what it's equal to, though. So we said it was sort of accelerating and then stopping, accelerating and then stopping, accelerating and then stopping. So the average velocity would be that acceleration times that tau, say. Okay? So the acceleration is, well, F equals ma, and the F is the charge times the electric field. QE equals ma. So the acceleration of a charged particle Q in an electric field is just always QE over m. That's always the acceleration. You just have a charged particle moving. It's really just the force divided by the mass. So there's the acceleration, and then how fast it gets is tau. Right? It makes it up to tau, time. So we have that expression. Now, let's plug that into the microscopic current. So we said that the current, if you think of it as a flow of charged particles past some area, it depends on the density of the charged particles, how many there are per unit volume. It depends on their charge. It depends on the drift velocity, it depends on how fast they're going, and it depends on the area, the cross-sectional area of the wire. So all we have to do is plug in our Drude drift velocity in here for V drift. And we get, it's N times Q, and then it's Q E over M, tau. So there's V drift, and then times the area, like that. So Drude model into the microscopic current is like this, and then we can combine some things and move some things around. And what you'll see is we can write I over A, the current per unit area. That's what we called J before. That's the current density. Equals, let's see, so we have N, and we have the charge squared. Tau is there, all over the mass. And what we're left with is E. And you can see it makes Ohm's law. J, the current density equals something times E, and this something is the conductivity. So now the Drude model has given us a microscopic expression for the conductivity. Sigma, the electrical conductivity, not the surface charge density in this case, is N Q squared tau over the mass. That is a conductivity. It's an ivity. That means it's an inherent property. It is an intrinsic property. It's not an extrinsic property. It doesn't depend on size or anything. It just depends on intrinsic things. Let's see if it makes sense to us. N, the volume density of charge carriers. Well, the conductivity should increase with N, yes. How much charge they carry? Yes, the conductivity should increase. How long they go before they collide? Yes, the conductivity should increase. And the mass in the denominator, that makes sense. Because the lighter they are, the faster they'll move, the more mobile they'll be. So this is conductivity. Sometimes we use the resistivity, and that's simply 1 over the conductivity. It's M over N Q squared tau. So those two we use sort of interchangeably. So you can see that Drude model gives you an answer that kind of makes sense. And if we worked out the units even work out as well. And I can see we have a question then about the Drude model. And MT knife, shouldn't the drift velocity be half of that? Drift velocity be half. Oh, yes, I know what they mean, yes. Yes, the drift velocity shouldn't be half. What they're referring to, and you probably saw this as well, is that we were plotting the velocity versus time, and we said, oh, it comes up and then it collides, and then we go up and bang, we collide, and we go up and bang, we collide. Like that. And we were calculating the average velocity you get to if this is tau. So yes, the average velocity is actually down here. It's not this acceleration times tau, it's 1/2 of that. But if you look in a condensed matter physics textbook, this is the Drude model expression. And the reason is, a little trick in here, this isn't really how you define tau. That's 2 tau. The definition of tau is if you're in some point anywhere in time here, then tau is the average time from the previous collision and the average time until the next collision. So actually that's our definition of tau that makes a factor of 2 appear and disappear. But in the end, you get the same thing. So if you define this as 2 tau and you put in the half up here, same thing. So just to not create confusion, I just called it tau at the beginning. But for those of you watching every factor of 2, that's what's going on. We can get a little more insight into resistivity and conductivity if we look a little bit more carefully at let's see what did this mean? Carriers, what did we call it? We said collide with the lattice. So we had this idea that they feel electric field, their velocity increases, they're accelerated, and then boom, they hit the lattice and they stop. And they go and hit the lattice, go, hit the lattice. So what's really happening? So let's imagine electrons in metal. That's our most common conductor that we study, and we know that metals are crystalline, so they have their atoms arranged in a periodic array like this, and they have these electrons that are free to wander around. That's what makes them a conductor. But what we haven't said yet is that the electrons travel as waves that move in between the atoms and don't hit them. Okay. A lot of high-level physicists and professors that see this are just completely appalled that I would say that, because this statement is not meant for them. This statement is meant for someone just learning physics. So if you do the quantum mechanics and the solid state physics, you learn that electrons do travel as waves. And they travel with a wavelength that sort of depends on this periodic potential created by the atoms. And you can't really think of them as billiard balls. They're kind of like waves, and they're kind of like billiard balls. So it's not really that billiard balls are moving in between the atoms. Okay? But it is true that the waves move through this lattice, and they would never collide with it. In this ideal case, all metals would be superconductors. The tau would be infinity. The wave, the electron, would just go through here, happily move along at very specific wavelengths, and would never hit the lattice. Okay? That's the ideal scenario. But that's not really what's happening. We know that metals actually do have some resistance. It's kind of small. But what really happens is that electrons collide with a vibrating lattice. So the lattice is never ideal, because when you're at a finite temperature, everything that's at some finite temperature has some amount of thermal energy. So we know that these things are actually they're vibrating. And they're not all vibrating together. If they were all vibrating together, you could still think of it as a periodic potential. But they're vibrating in different directions and with different frequencies, with thermal noise, all this stuff. So the electrons aren't actually moving through a perfect lattice. They're moving through a slightly deformed lattice. And that is why the resistivity depends on, that's why you have some resistivity. And it's also why it depends on temperature. So if we were going to think about what is rho versus T, so here's temperature, and here's rho, the resistivity. If you want to plot it, the way it's usually given to you is actually based on the change from some point. So you start out and you say, I happen to actually know the value of rho at a certain temperature. So at some temperature T naught, I know the value of rho at rho naught, and then the way it's characterized is with the temperature coefficient of resistance. Which is called, the fancy name for something that we symbol is alpha. Okay? So all it really is telling you is alpha is kind of like the slope. The way the formula is usually written, or one way you could write it, is that rho at some temperature equals rho naught plus, and then you got to take that rho naught and multiply it by alpha and by T minus T naught. So it's just telling you for every change in degree of temperature and change in Kelvin, you multiply this alpha. It's usually really small. It's sort of 5 times 10 to the, I think around -3. Depends on the material, of course. So it's not very big. You multiply that by the original rho, and that's how much of a change you get from somewhere else. So it's always sort of a linear thing like that. Now, this is just an approximation. It's not really linear over all temperatures, but over some small temperature range, if you know rho at some temperature range, it'll be approximately linear around that point. And this is the formula, and this is the thing that characterizes your material. And if we look at that, that would be in inverse kelvins. Right? Because it's just some factor you multiply by the temperature change in Kelvin to multiply the resistivity to give you the change in resistivity. So, but you can see why it depends on temperature, is because those collisions that stop the charge carrier are due to the atoms being in the wrong place due to thermal vibration. It'll also show you why we can use current to heat something up. If you pass a big current through something, then the electrons will move along, and when they hit an atom that's a little bit out of place due to thermal vibrations, they give it even more energy. Right? They dump their kinetic energy into the lattice. So again, that's two ways that electric current and temperature are connected.